We begin by talking about what's a slope field. So let's look at a very straightforward differential equations. dy dx equal to 2x. If we resolve this, we'll find that the solution is x squared plus c, and this solution is what we call an analytical solution because these functions satisfy these particular differential equations, and we got it by integration and so on. But there are other ways to resolve these differential equations. One of it would be a graphical, the other one is a numerical. And our focus for this will be a graphical for this particular video, because a slope field would be the graphical solution of differential equations. So we'll look at a couple of examples here. To understand how slope field is obtained is, I will discuss one example, the same differential equation again. And if we solve this analytically, we'll get y equivalent to x squared plus c. We don't know what c is. However, suppose a list of initial conditions are given. So I'll create a table to show you the whole idea now. So say you are given some initial values. Let's say when x equals 0, y equals to -2, you're probably given this also. X equals to 0, y equals to -1, and so on. So if you resolve this, substitute into this solution, you get the corresponding c values, and the c values would be here. You get this c values using these initial conditions. Of course, substituting the c values, you get the functions, the solution that is, and you can use the x value also, will be all 0, 0, 0 here, and calculate the y prime, that here it is. So you will get the corresponding, I think you get 0 over in these particular examples, because the reason is x 0, you substitute back into the y prime and you get 0. So this is a corresponding y prime for all x values, but you see the different functions look different. So what do we do now? So you may begin by constructing the little tangent of the segment that has this particular slope, but at these values here. I'll show you how. Let us finish constructing the diagram first. So all these initial values telling us that when x equals to 0, y is equal to -2, and the spot we're talking about is right here. And the slope at that particular point is 0. So you expect to see something like a flat line, a horizontal line like this, but all we need is just a part of it. So we draw a short tangent segment like this, okay? And similarly, when x is 0, y is -1. So the point we're talking about is somewhere right here. And the gradient or slope is 0. So again, you do the same at the point, but you do a little thing like this. Not a long line, but a segment. Similarly, when this is 0, the y is 0, 2, and the gradient is 0, you do this little thing. And finally, you from the table, I can do one more here. You suspect that if you if you use different initial conditions, you get different c values in the function, and of course you get obtain a different slope for this point, and you do the same, and you then sketch those points. Okay, not it's a slope, a short segment of the tangent line to the curve actually. So eventually you end up seeing something like this. So that's the whole idea that is. In the next example, we'll look at how we can sketch a solution curve when the slope field is actually given to you. So here, differential equation is given here, and the initial condition is when x is 0, y is 1. So the first step is that, okay, take a look at the whole idea of the curve. It seems to have this notion is doing something like this. And the next thing you want to do is to sketch this point here, the solution, then it will be here, somewhere right here. You can see that at this particular point, all this little segment of tangent is pretty steep. It looks a bit like this. Again, you move on to the next column. Maybe you see that, okay, they all go like this way. Okay. So I suspect that maybe you can sketch something like this, and then the next one look a bit like this way, going this way, tangent. So I suspect that, okay, perhaps you can sketch something like this, and continue this whole idea. Sketch somewhere here, and then again something like that. Something like that, just following the same orientation as all the other segment of tangents, and perhaps something like that, and go on, and so on, and of course to the left, suspect something like this. So in the end, most probably we're going to see something like this as a solution curve to the differential equation. And with the initial conditions given. Remember this, we must pass the curve through the point 0, 1. And here I use an applications software to generate the solution curve, which passes through 0, 1, and compare this to the curve I've drawn. Not too bad, actually. If you take a look at this and compare this. The idea is that as long as your curve must passes through the initial condition 0, 1, the general shape of the curve is there, that should be okay.